Diffusion models. So these diffusion models are a machine learning technique used to generate or transform images, text and other data types. So in simple terms, diffusion model works by gradually adding noise to that input data point and then gradually undoing that noise to reconstruct that original data point. And this process is repeated many times to train the model and improve its ability to generate or transform data. To understand this better, let's consider you have taken a text. So you'll start with a piece of text. For example, the quick brown fox jumps over the lazy dog. So the diffusion model will first add the noise to the text, for example, by randomly swapping the words or changing letters. And then model will attempt to reconstruct the original text by undoing that noise. And this process is repeated many times and the model learns to generate text that is similar to original input. So over time, the model will learn to generate text that is coherent and grammatically correct. This is because the process of adding and undoing noise helps the model learn the patterns and relations between the words in the input text. Another example can be found in the field of image generation. That is, a diffusion model could be trained on a large data set of images and then can be used to generate new images that are similar to that training data set. And here the model will gradually add noise to that initial blank canvas and then will remove that noise to produce a new image. Now, how this diffusion models work? So they generally work by gradually adding the noise to that input data points and then remove that noise in order to reconstruct the original data point. So first, in order to make this diffusion model, first we will start with the input data point, which could be an image, a piece of text or any type of data. Then we add the noise to the data set, such as randomly swapping words in a sentence or adding some random colors to that image. This process is called denoising. Then we'll learn to remove the noise. That is, after adding noise, the model attempts to reconstruct that original data points by removing this added noise, which is called reconstruction, and then repeat that process and finally fine tune this. Once model has been trained, it can be fine tuned for specific tasks such as generating new images or text. So over time, the model will learn to generate text that is coherent and grammatically correct. So in summary, diffusion models are a powerful technique for generating and transforming data by gradually adding and undoing noise to that input data, which allows the model to learn patterns and relations in the data. And these models are used in variety of applications such as text generation, image generation, and data compression. Now, what's the difference between these popular generative models? Because they all are generating the data, be it GAN, virtual autoencoder, flow-based models, and diffusion models. So let's try to understand this. First, take GANs. So these generative adversarial networks are a type of generative models that consist of two neural networks, a generator and a discriminator. Now this generator will create synthetic examples, be it images or videos, while the discriminator will evaluate whether that generated example looks real or fake. Now generator and discriminator are trained simultaneously in an adversarial manner, with the generator improving its ability to create realistic images and the discriminator improving its ability to distinguish real from fake. For example, GAN can be trained on a data set of animal images, where the generator would learn to create new unseen animals, while the discriminator would learn to distinguish between real and generated images. Then comes variational autoencoders. These are the generative models that learn to compress data in a lower dimensional latent space. So it consists of encoder and a decoder, where the encoder learns to compress that input data into latent representation and the decoder reconstruct that original input from the latent representation. For example, this virtual autoencoder can be trained on a data set of handwritten digits, where the encoder would learn to compress that digit into a latent representation and decoder would learn to reconstruct that original handwritten digits from their representation. Then comes flow-based models. So these flow-based models, they use invertible transformation or the mathematical functions that can be reversed to generate new examples. So these models learn a mapping from a simple low dimensional prior distributions. So for example, a flow-based model can be trained on a data set of faces. So where the model would learn to generate new unseen faces by applying a series of invertible transformation to a simple low-dimensional prior distribution. And then we have diffusion models, which are a type of GANs that work by gradually adding noise to that clean input and then removing that noise to reconstruct the original input. For example, diffusion model can be trained on a data set of images where the model would learn to generate new unseen images by gradually adding noise to a clean image and then removing that noise in order to reconstruct the original image. So these all models has its own strength and its weakness. Then comes a Sora diffusion transformation model. As we are talking about the diffusion model, so we'll take an example of this. Nowadays, the Sora is a cutting edge machine learning model which takes this written text as input and generates the compelling videos as output. So it is a text to video generator which can create videos based on descriptions, scripts or text prompts. So let us try to understand this by calculating the Sora diffusion transformer by hand. So this OpenAI Sora is based on diffusion transformer model. So where we have a goal to generate that video which is conditioned by text prompt and a series of diffusion steps. So first we have given a video and given a prompt that is Sora is sky. And we are given a diffusion step that is t is equals to 3. So first step is to convert this video into the patches. That is, we will divide all that pixels in all frames into 4 time space patches. So here for example, we are given this 1001. So we'll write it in one row, 1001. Here we have written 2010, here 0130, here this much. Okay. The second step is a visual encoder. That is, we will take this pixels to the latent image. That is, we will multiply the patches with the weights and biases followed by ReLU. And the result is a latent feature per patch. The purpose is a dimensionality reduction. So that is, we will just simply multiply this form and we will use the formula y is equals to wx plus b. W and b are the weights and the biases, right? So here if we check, the number of columns are 1, 2, 3, 4. Here the number of rows are 1, 2, 3, 4. So just do the element wise multiplication. 1, 0 minus 1, 0 multiplied with 1, 2, 0, 0. Adding 0 bias here will get 1 here, right? So this way we'll do the matrix multiplications and we'll get the results like this. And now we are using the ReLU. So all these negative terms would be converted to 0. So the answer will be 1, 0, 0, 1, 3, 2, 6, 1 like this, right? Next, we will add the noise. So you will sample a noise according to this diffusion step. So typically larger this T. So here we are, the smaller the noise. We have taken T small. Okay, so you will add a sample noise to that latent features in order to obtain that noise latent. And the goal is for purposely adding noise to that video and asking the model to guess what the noise is. And this is analogous to training a language model by purposely detecting a word and asking the model to guess what the deleted word was. So here you have added some sample noise, right? Now you will do the addition here. So 1 plus 0 will be 1, 3 minus 1 will be 2, 0 plus 2 is 2, like this 0 plus 1. So just do the multiplications of this one, this and this. Okay, and you will get this here. And then subtract. So from this minus this, so you will get the results like this, right? So when you will subtract 1 minus 0, you will get 1 here, 2 minus minus plus 4 here, right? You have got the things like this. And then you have a visual decoder here. So in this visual decoder, you will do the element wise multiplication. Check the number of columns as 2. Here the number of rows is 1. So 1, 1 will be multiplied by 1, 0. Adding 1 here will get the 2 here, right? So this we will do. Then we will have conditioning by adaptive layers. So encode that condition. Sora is sky. So you will encode it in a say 0, 1, minus 1. You have done that, right? And encode this T3 to a binary vector, say 1, 1, right? And concatenate the vectors in a 5-row column. So we have got 1, 1. And here we have taken 0, 1, minus 1. So it becomes the 5 row, right? 5 rows are there. And then we have given a adaptive a layer norm. So here if we check, the number of columns are 6, and here the number of rows are 5. So just multiply this with this one. We will use the formula y is equals to wx plus b. So we will do element wise multiplication, that is 1 0 0 1 0 multiplied by 1 1 0 1 minus 1, adding 0 here will get 2, right? Then we will get the things. We will estimate scale and shift, that is we will multiply the combined vectors with the weights and biases. The goal is to scale and shift, right? So we have got this 2 1 minus 1. Okay, then we will take this much, that is we have taken 2 and minus 1 here, and this 1 and 5 here, right? Above 2 here, this much. We are doing scaling and shifting, that is we are multiplying this by 2 and adding this one. So 2 into 1 plus minus 1, that is 1 here, right? So 2, say we take the this one, 2 into 2 4 minus 1, that is 3 here, right? We will get this matrix by scaling and shifting, and then we have got this. And now we have a query key, that is we are having a transformer that where we have self attention. We will feed this condition noise latent to a query key function. So here when we have got this matrix, so check the number of columns 1 2 3 4. Here the number of rows are 4. So just do the element wise multiplication, that is 1 3 1 1 1 minus 1 multiplied by 1 1 0 1. So it shall be 1 plus 3 4 here, right? Up to this we'll get. So we'll get this matrix. Then we will have this pointwise FFN. So here also we'll use this formula y is equals to wx plus b. So here check the number of rows as 2, the number of columns as 3. So 1 minus 1 1, multiply this with the 4 and 6, minus 1 into 4 plus 6 into 1, adding minus 2 here will get 0. So we'll get this matrix here. So up to this we're done. Next we will train the things. So here we will calculate this MSC loss gradient by taking the difference between the predicted noise and the sample noise, which is a ground truth. So you will use the loss gradients to kick off the back propagation to update all the learnable parameters. And note that visual encoder and decoder parameters are frozen. So here you have taken the sample noise here. So sample noise is taken from there, na? So you have just taken this matrix here, and you have got this matrix, right? So you will simply subtract both these matrices, this and this. So 0 minus 0 0, 1 minus 1 plus 1 minus minus plus 1. So 1 shall be 2. So you have got this thing, right? So MSC loss gradients. And finally we will get this patches into the videos, that is we will rearrange the patches in a sequence of video frames. So here after visual decoding, whatever we got, we have converted into the patches, that is we are taking it first patch 2 5 1 3, then we are taking second patch as 1 3 5 4. So we are taking second row as this much, then we are having the third row 2 7 4 2. So we have given it in the form 2 7 4 2. The last is 0 0 6 6, because we are using ReLU. In the ReLU the negative terms are considered 0, so it shall be 0 0 6 6. So to summarize this, we are given a training video, or we are given a prompt here, right? First we have converted the space-time patches like this we have done. Then we have done individual matrix multiplications. Then we have added sample noise, done the simple addition there. Then we have got this matrix here, right? Then we have predicted this noise, we have individual element wise matrix multiplication. So like this, we are for this we are using the formula y is equals to wx plus b here. Now what are the applications of diffusion models? So this diffusion models have a wide range of applications, including text generation, video generation, text compression and more. So first can be text generation. So these diffusion models can be used to generate the coherent and realistic text. For example, a model trained on large corpus of books that could generate news stories or articles. Then image generation. So where a model trained on a data set of paintings could generate new paintings in the style of artist in the data set. Then data compression. So by learning the patterns and relations in the data, diffusion model can represent the data with fewer bits while still preserving important information. then video synthesis and music generation, then protein folding predictions, and finally natural language processing. So where diffusion models can be used for tasks like language translation, text summarization, sentiment analysis. And these are just few examples of many applications of diffusion model. So as the field continues to grow, new and exciting applications are likely to emerge. Thank you.